Alright, we got a rigid body right here. So these are all connected to each other. And we're going to find out the angular momentum of the whole system. So they give the position, the mass of each, or the position of each mass, and then the vector that it's rotating about, the angular velocity vector. Okay, but to start off, this may seem complicated at first because there's a little diagram to show you. So we got some origin, and then there's going to be a chance, or there's potential for this entire mass itself to have some type of rotational motion, which would give it its own angular momentum. But then this mass itself is allowed to rotate also, so it could also have an angular momentum. But in the end, I'm gonna skip ahead just to show you. In the end, it turns out to be very simple because you have your r cross p, which is your linear angular momentum, and then you have the actual internal angular momentum. Okay, so which is going to be about the center of mass right here. Okay, so you have the center of mass, its own r cross p, and then the individual rotational angular momentum about this point. And we've also broken this right here. R sub a is equal to the center of mass plus r prime. So basically r prime is just the position with respect to center of mass. Okay, so just looking quickly here, you have your classic r cross p, which is broken down to r cross p again. This is momentum. A summation of each angular momentum forms the total. Okay, and then when you expand it out, it gets complicated, but things simplify. Some terms go away, and you get, like I said, this term again, which is just the combination of the linear plus the internal angular momentum. Okay. Now in the problem though, I said we have four masses, and it wants to know, or they're asking the total angular momentum. You can't just use these positions right here for this term right here, because this, remember, is the position of each mass with respect to the center of mass, not the origin. Okay, these right here, these vectors represent the position with respect to the origin. Okay, so I'm gonna skip over to the book just to show you one last time. We have r cross m times r dot, which is just r cross p, and you can see that again right here, again with respect to the center of mass. And then as you expand it out, this is going to get complicated, but r cross p you can follow. Move the m over because it's constant. We get this term right here, which when expanded out, same thing again. When expanded out, you get this little expression right here. Okay, and this is without the mass multiplied by it. So you see this is just the r cross omega cross r, r cross omega cross r. There's no mass term on there. Okay, but on the test, to figure out the angular momentum, you would not simply plug in, like I said, these terms right here. You would have to figure out what the position of these masses are with respect to the center of mass, which I've done here. I've calculated the center of mass right here, and then here I've written down the four vector position terms, but then R prime is with respect to the center of mass. I've rewritten these vectors in terms of prime, so A prime, B prime, which is simply the vector A minus the center of mass right here, B minus center of mass, and so on, to get these terms. Now that all that's done, to find the actual angular momentum, we would just use all of the A prime, B prime, and so on, and plug these in to these terms right here. Okay, so I'm not going to do it in this video, but I'll probably be remaking a video where I actually work the full problem out. But the important thing to know is you can't just use this equation right here and then plug in these vectors, because remember, these vectors are with respect to the origin. So when you write the total angular momentum, you have to figure out the center of mass, cross it with the momentum of the center of mass, and then remember, just use these prime terms, not these terms right here. All right.